Well, the most important ones, the most widely used, are really alloys of iron, alloys of copper, and alloys of aluminum. Those are the three big ones. The one class of metals that has the most industrial and practical use in our civilization are alloys of iron. Silicon and carbon are the principal ingredients in carbon steel that gives it additional strength and hardness and other properties. More highly alloyed iron-based alloys, and there are elements like chromium, nickel, molybdenum, vanadium are probably the most common alloying elements. One good example is the whole category of stainless steel.
Mhm.
And stainless steel, which was developed in the 1920s and 30s, the principal alloying elements in stainless steel are chromium and nickel. Let's face it, just plain old cast iron or carbon steel, if it's out in the elements or exposed to salt water and things like that, it's going to pretty rapidly corrode. And so it was discovered that by the addition of mainly chromium, but also nickel, you can dramatically improve the corrosion resistance of steel, and that's what brought about the category of stainless steel. A good example that I became aware of a while back. I was at a company up in the upstate of South Carolina. Palmetto Plating is the name of it, and there they were processing valves for the New York City freshwater system. And the reason's obvious. First of all, you don't want contamination and rust and corrosion products flowing through your freshwater system.
Right.
But also, you really don't want to go back in the next few years and dig up the streets of New York City to install new pipes and valves and so on. Well, how do you get valves and pipes and things to last 100 years under the ground? Well, the whole system will be manufactured from stainless steel. Actually, if you really look at what they're putting in there, which is a 316 stainless steel, barring an earthquake or a nuclear attack, that freshwater system will probably be there for many hundreds of years. The corrosion resistance of 316 is pretty phenomenal. The chemical composition, of course, is fundamentally important to determine the properties of a metal. In this case, I guess we're mostly talking about steel, but it pretty much applies across the board. It turns out that there's a process called heat treatment that has a dramatic effect on the properties of steel. And heat treatment is basically defined as the controlled thermal processing of heating and cooling that results in desired improvements in properties.
Mhm.
And the most common one is with steel is heating the steel up to its transition temperature, where the steel will become more it'll become more susceptible to dissolved carbon, basically, because the amount of carbon that's in solution in steel determines what its hardness and strength is, pretty much. So if I heat steel, most carbon steels, for example, if they're heated above 1550 degrees Fahrenheit, they become non-magnetic, first of all, and that steel or that iron transitions from body-centered cubic crystalline structure to face-centered cubic. And in the parlance of metallurgy, at that elevated temperature, it's called the gamma phase. Most phases of metals relate to the crystalline structure. So at that elevated temperature, you have something called gamma phase. And below that critical temperature of 1550, you have something called primarily alpha phase. In the gamma phase, gamma can dissolve more carbon in solution than alpha can. And then the trick is, it's an age-old trick from even ancient times. If that if that gamma phase, which is now dissolved more carbon than it can dissolve at say room temperature, if it's cooled down very rapidly, so-called non-equilibrium cooling. So if you take a piece of steel, for example, and heat it up till it's bright red, and then you stick it in a bucket of water, the carbon doesn't have time to diffuse out. So you have something called a supersaturated condition where there's more carbon in the lattice of the crystal than could be contained there under equilibrium cooling. If you allowed that steel to cool down very slowly, the carbon would come back out of solution. It's what it wants to do. It's its lowest energy state. But now you've quenched it in say water or oil. You've cooled it down very rapidly. Now you've trapped an excess of carbon in the lattice, and you've distorted the crystalline structure into something other than body center cubic, and it's going to become something. Typically in a crystalline structure, it's going to be probably orthorhombic. It's going to have a very different shape, and it's going to be in a very high stress state because of that carbon that's stuck in there. Right. And that's where the term interstitial compound comes from, because the carbon is trapped. The carbon is trapped in the interstices. That is to say, the spaces between the iron atoms are where the carbon resides, and now that carbon is trapped in there. And when the steel transforms, the crystalline structure transforms. It wants to go to body center cubic, but it can't because the carbon's stuck in the way, and so that's how you end up with hardened steel, is essentially by trapping carbon in the lattice or in the spaces between the iron atoms. Interesting. Elon Musk is obviously a pretty knowledgeable and his companies are pretty innovative in the world of materials. His engineering team, they looked at all these fancy composites, which are obviously very lightweight and all that, but when they looked at what it would cost to build these rockets from carbon composites and things like that, and titanium, they also looked at what's called 400 series stainless, which is a pretty inexpensive grade of stainless steel, but it also is very weldable. It's very amenable to fabrication to assemble by welding. Gotcha. And of course, they wanted to use very automated and fast welding techniques to weld the pieces together. And so that's what they settled on. That's a material that's been around for probably 100 years.